Hello everyone. So we are at the topic of transistor amplifiers, and today we are going to develop a small signal model for BJT amplifiers. Let's consider a conceptual amplifier circuit using an NPN BJT transistor in this figure. And first, we're going to calculate the DC bias point for this circuit by setting the AC signal, or small VBE, setting it to 0. So collector current can be calculated from this equation, and in this equation, the early effect is neglected. In other words, lambda is equal to 0, or VA equals to infinity. If you want to consider the early effect, you're going to use this equation, IS e to the VBE over VT multiplied by 1 plus lambda VCE, which is the same thing as IS e to the VBE over VT multiplied by 1 plus VCE divided by VA. VT in this equation is the thermal voltage, and the value of VT, or thermal voltage, is about 26 millivolts in room temperature. IS is the saturation current. So let's continue doing the calculations, assuming that there is no early effect, or lambda is equal to 0. So because I want to use the BJT in the active region, so that I can have a linear transfer function from this BJT, I can calculate I base, or base current, as IC divided by beta. And emitter current, or IE, is going to be beta plus 1 divided by beta multiplied by IC. These are the DC current equations for the transistor when it operates in the active region. And from the collector emitter KVL, I can write collector emitter voltage equals to VCC minus RC times RC. So now when a signal base emitter is applied to the transistor, the total instantaneous base to emitter voltage, or small b sub uppercase BE, is going to be equal to the DC part of base emitter voltage plus AC part of base emitter voltage. This is what I have here. The total base emitter voltage consists of a DC part and AC part. So I'm going to plug this voltage in the IC equation, the total instantaneous collector current equation here. And this is my total base emitter voltage. I have this total equation, two parts, substituting these two parts to the base emitter voltage. So if you do so, you're going to end up with this equation, and I know that e to the power of a plus b is equal to e to the power of a multiplied by e to the power of b. So I can reduce this equation into this format, and by doing so, I can, if you compare this equation by the previous one that I had for DC collector current, this one, you're gonna see that this is the DC part of total IC equation. So this is my uppercase IC, and the rest is what is related to the AC part of total current. So I'm going to have the total instantaneous current, small I sub c, equals to uppercase IC, or the DC part of collector current, multiplied by an exponential that is dependent on the signal base emitter voltage. So this is the total IC instantaneous collector current that I had before. Now I can use the Taylor series expansion to expand this exponential equation. And in this expansion, if a base emitter signal voltage is much smaller than terminal voltage, so if this condition applies, you can neglect the higher order terms in the exponential series expansion, and you can keep only the first two terms. So if you do so, IC is going to be almost equal to the total IC is going to be almost equal to DC part multiplied by 1 plus AC and base emitter voltage divided by VT. This equation is taken from the Taylor series expansion of this top equation and by neglecting the higher order terms. So under small signal approximations for BJT, meaning if signal base emitter voltage is much smaller than threshold thermal voltage, you can write total instantaneous collector current. This is bias plus signal current equals to a DC signal, a DC current plus an AC current. A coefficient multiplied by AC voltage applied to the base of this transistor. So if I can write this in terms of DC part of the collector current plus AC part of the collector current, and comparing these two equations, I can find the AC part of the total collector current, and this is going to be the AC part of my collector current. Okay. This equation relates the signal current in the collector to the corresponding base emitter signal voltage. It can be written as IC equals to GM times VBE, and here GM is the transconductance of the amplifier, and it can be calculated as and it is equal to I collector DC collector current divided by thermal voltage. So now that I have written collector current, the total collector current, as a summation of DC part of collector current plus AC part of this current, I can find the total base current and can write the total base current in terms of its DC part plus AC part. The only thing you need to do is to divide this IC by beta, because I know that I base equals to I collector divided by beta, because I want the transistor to operate in the active region. So if you do so, compare this equation with this one, and then that's going to give you the signal part of base current. So the signal base current is equal to 1 over beta IC divided by VT multiplied by base emitter voltage, which is equal to GM over beta times voltage of base emitter, signal voltage from base to emitter. The small signal input resistance between the base and emitter is denoted by R pi and is defined as base emitter voltage divided by base current. So R pi is going to be equal to beta divided by GM, or transconductance, and that's equal to thermal voltage divided by DC base current. Let's take a look at calculation of voltage gain or AC voltage gain in this amplifier configuration. And remember that we neglected the early effect in these calculations from the beginning. So collector emitter voltage, or the total signal plus bias collector emitter voltage, is equal to VCC. This is my voltage, DC voltage source, VCC minus IC times RC, and that's equal to, I'm going to replace IC with its DC and AC components, signal and bias components. And if you do so by collecting the DC parts together and separating DC and AC parts, you're going to have a completely DC part and an AC part for your total collector emitter voltage. So that's going to tell me that the AC signal, the signal voltage, collector emitter voltage, so that's going to tell me that signal collector emitter voltage is equal to the signal current multiplied by RC, and I know the value of the signal collector current, which is equal to GM VBE, and from there I have the voltage gain of this amplifier, which is negative GM multiplied by RC. So the signal gain of the amplifier depends on GM, which in turn depends on the DC collector current. So the AC gain of the amplifier, or the signal gain of the amplifier, depends on the bias point of this amplifier. So using the equations that we derived for the signal applied to this amplifier, we can model the BJT for the signal circuit. So looking at this equation, there is a path, there is a resistance between base and emitter, and the value of that resistance is R pi, and the voltage across that resistor is VBE. And the collector current, it depends on the base emitter voltage by a factor called transconductance, or GM. So I can model this dependence using a voltage dependent current source, as you can see here, and the value of that current source, dependent current source, is equal to GM times VBE. So our model is not complete, it is missing something, and that's the effect of collector to emitter voltage on the collector current, or the early effect. So I can model that effect by adding a resistor, this R sub O, between the collector and emitter. Now my collector current, the model for collector current is complete. So IC has two components in it. One component comes from the base emitter voltage, and one component takes into account the effect of collector to emitter voltage. So when VCE increases, IC is going to increase. This is my collector current. So in this model, GM is IC over VT, R sub O is VA, or early voltage, divided by IC, and VA is defined as 1 over lambda, and that's this VA is early voltage, and that's how to take into account the effect of the early effect in BJT. So R pi is beta divided by GM, and that's VT over I base, DC current, base current. And so I want to show that there are two models, there are two equivalent models for BJT small signal model, and in one of them I show the collector current as a voltage dependent. The collector current has one component of a collector current is a voltage dependent current source, which is this one, and I'm going to show that this is the same as current dependent current source. This is the derivation. GM VBE or GM V pi is equal to GM I base R pi, because this is the same as small VBE. I show it with VBE or V pi, they are the same, and that's equal to this GM I base R pi is GM R pi multiplied by I base. If you use this equation for R pi and this equation for GM, you're going to see that GM VBE is beta times IB. So you can consider a BJT amplifier as a voltage dependent current source or current dependent current source.